Hello and welcome. In this video, I'm going to talk about DOBIN, a dimension reduction method for outlier detection. This is joint work with Rob Hindman. To DOBIN means to inform against, maybe especially to the police. And that's a definition from the Collins Dictionary, and naming credits go to Rob. So, I've worked in outlier detection for some applications like intrusion detections and detecting outliers in water quality data, and a meta-learning study for outlier detection. But what I've noticed is that there are no dimension reduction methods specially done for outlier detection. And this causes some problems because high dimensional outliers may not be outliers when you project it into lower dimensions. So, for example, things like PCA may not really project outliers as outliers in a low dimensional space. Because that's not the purpose of PCA. So DOBIN is a distance-based outlier basis using neighbors. And what we do in DOBIN is we find a set of basis vectors tailored for outlier detection. So the way we find it is that the first basis vector is in the direction of the highest outlierness. The second basis vector is in the second highest direction of outlierness, and so on. And then we find a set of basis vectors. So one of the most important parts of DOBIN is the Y space. So we are given the original data set, which we call the X space, and from the X space we compute this Y space. So what is the Y space? So for every point in the X space, we find k nearest neighbors. So for every X, we find Z1, Z2 up to Zk. And then so if the coordinates of X are X1 to Xn, and for the coordinates of Zi is Zi1 to Zin, then we define Y like this. So that is X1 minus Zi1 squared. So this is in the first axis. In the first axis, we take the two coordinates, take the difference and the difference squared. And then in the nth axis, so we do this for every axis, for in the nth axis, xn minus zin squared. So if we write this in a shorter notation, what we do is we have the element-wise squares, the element-wise difference squares. So x minus z1, where x was this, and z it should be zi, element-wise squares. So the Y space is an interdistance space. So if X is in Rn, Y is in Rn plus, because everything will be positive. And what then we do is we remove all points with very small distances. So if we have y1 plus y2 plus yl for a given point y, if they're smaller than some number, then we remove those points. Because why do we remove them? We remove them because we want to find the directions of highest y. So we don't want it to be clogged down by the points that are very close to each other. So that's the reason for removing all the y points with very small interdistances. So here's an example. This is our X space, a 2D X space with one artificial outlier there. This is our Y space. So for every point, it will take some number of points, maybe 10 or maybe 5 or so. For every point, it'll take some neighborhood, and then it'll compute the distances, and it'll take the distance squares in each direction, and we get this space. So for the red point, see, if we take 5 points or 6 points, then that'll be one of the closest points. So we get that distance squared and that distance squares, and it'll give rise to a point like that. And that distance would give you another point, and so on. So because we're removing, so this will have a lot of points close to 0, 0, and we'll remove those points and we're left with that. So what we see is the outliers kind of gets exemplified. So we are kind of, putting a spotlight on the outliers. So just to give a brief comparison on the X space and the Y space, X space is a point in the X space is an input observation, whereas a point in the Y space gives this interdistance vector between two neighboring points that are in the X space. So in the X space, distance is not a linear combination of the X coordinates, but in the Y space, that's the key. The distance in X is a linear combination of the Y coordinates. So let's talk about distances. So distance between 2 points is, if we call it distance between xi and xj squared, we can write it as xi minus xj transpose times xi minus xj. But more generally, we can write the distances with a matrix in here, S, where S is a symmetric positive definite matrix. So now we can kind of write it, we can write it like this, using an inner product where eta is inner product, and this is the element y squares. So xi minus xj element y is a square. So if you use that, we can write the distance like that, because if we use a symmetric positive definite matrix, we have you can diagonalize it and get a vector eta, and there is a reason to write it like that. So in the Y space, using the Y space notation, we can write it as eta minus some y vector, yi. So that's your distance. So you can write the distance using the dot product or the inner product generally in the Y space, right? And you can, like, if you want the sum of all the distances, the distances between these neighbor points, you can write it like that. And why is that important? That's important because we can maximize the sum of distances between points. So we can find we can find a direction. Now that is the eta. Eta is the direction in which the points between distances are maximized. So we can find this direction eta, where the points between these distances are maximized. We can sum up all the distances and say in this direction the sum of the interpoint distances is maximized, and we do put a constraint that the length of eta is 1. So we can do that. So geometrically, what does this mean? We have the X space, and when we transform this, we get our Y space. And what we are finding is this direction eta, given in this yellow vector. We want the direction eta such that eta dotted YL is that vector for every point there. Eta dot product YL, that is actually when you project these points that distance, because eta is a unit vector, even though this is the direction of eta. So eta is a unit vector. So when you project that vector, that is, you are going to get this sum. You add that, you add that, you add that part, and you keep on adding all the points when you project it onto that direction, to that vector. And when you add it up, you're going to get some number, and you're finding the eta, that direction eta, where that sum is maximized. That is what we are doing, right? So that's the transition space, the Y space. So we can solve it using Lagrange multipliers. When we solve it, we get this expression for eta, which is eta is the sum of all the y vectors divided by the length of that sum. So that's good. We found the direction that maximizes the distance between points, but we found the eta. But from one eta, how do you get a basis? So we want n etas like that. Well, that's not too difficult, because what we can do is we have this eta, and we can find a vector that's perpendicular to eta. And so we know the first eta. We know for every y we have a component, a parallel component and a perpendicular component. So what we do is, from all y we find the y perp, the y perpendicular component. So from y we remove the parallel components, and all y perps are perpendicular to our eta, which we are going to call eta 1. And we do the same procedure for all y perps. So for all y perps, we find eta 2 by doing the same procedure in the y perp space. So our eta 2 is perpendicular to eta 1. And we continue this way. So for the third vector, we take the parallel part to eta 2, and then we continue this way and we get eta 3, and so on, and we get the full basis. So that's the mathematical foundation for DOBIN. All maths finished after that. So how do we test DOBIN? We test DOBIN by using O3 plots, because we need something to compare to see, okay, is this projection a good projection? How do we test that? We use it by using O3 plots, and O3 plots are in the Outliers O3 package done by Anthony Unwin. And the O3 plot has, it uses an ensemble of outlier methods. And it also does different things. It finds outliers using this ensemble on a full data set, and also it does it on a combination of variables, so on different subspaces of the data set. So this is a data set from Anthony Unwin's paper. So this is the election 2005 data set, which is in the R package MB graphic, and so they take four variables. So the way the so this is the O3 plot, and that's the DOBIN plot. So let's go over the O3 plot first. So the way the O3 plot works is, it first so on the left hand side we have the variables. So we have the car ownership, area, birth rate, population density. These are variables, and the colors, what they means is, the first row just uses population density, so it's only using one variable. Like this row uses car ownership and population density. And what are all these? These are the observations. So x138 is an observation, x84 is an observation, and so on. And so what are the colors? The colors are, if something is, in this one, color, if a block is colored in yellow, then that means that observation is identified by as an outlier by five outlier methods. So for example, x84, when you just consider population density just in that variable, so you're just considering population density, x84 is identified as an outlier. x84 is identified as an outlier when you consider area and population density, and that's also done by 5 outlier methods. And if you look at this square here, if you consider birth rate and population density, x84 is identified as an outlier by 4 methods. And if you do all, so if you take the full data set, that's this last row here, x84 is identified as an outlier by 3 methods, and so on. So that's the way to interpret these O3 plots, right? So the more outlying observations generally come towards the right. The less outlying observations come towards the left. So for example, X138 has been identified as an outlier when you consider birth rate, but it's only identified as an outlier by one outlier method, right? And so that's the O3 plot and the DOBIN plot, which is what we are doing. So look at X84, and here we don't have the X's. So 84th observation comes way over here so this is the first DOBIN vector, which is eta1, and that's the second DOBIN vector, which is eta2. So X84 comes way as an outlier, like, you know, way outside in this axis. And then comes X76. X76 is here, right, in this one, and X83, which is there, and X82, which is there, and 221, which is the next one, and 21, which is there, and 87 and 81 both there. So we are getting this full block like that, very much kind of outside, but X84 is so outside when we project it in this space. So that's what we are getting. So the next example is using time series data. So to use DOBIN, DOBIN is needs to be used on independent observation. So we are generally having a rectangular data set in our mind. So this is the time series data from the TSDL package, and it's a stream flow near it's Mad River near Springfield. So that's that data set, and here we have this massive spike. So we can't test the time series data directly using DOBIN and reduce dimensions to find outliers. But what we can do is we can convert the time series to, you know, we can find features using the time series. And these time series features we can feed into DOBIN, which is what we've done here. So we have so this is the time series data, and then we see this massive spike, and we hope that, you know, DOBIN will kind of isolate that, isolate some observation with that spike. So how do we do it? Is we convert the time series to windows, non-overlapping windows, and for each window find time series features using TS features package, and after we find the features, then we input it into DOBIN, and this is what we get. So here we have the first DOBIN vector and the second DOBIN vector, and that observation is seriously outlying from the rest. This is a projection, so we see that. And when we look at that observation comes from a time series window. So this window has, so this is the window that corresponds to that observation, the time series window. And you see here we have this spike which is greater than 75, and that's the only spike that's greater than 75. So we are getting a window somewhere close there, right? And the next example uses a graph. So this is a graph of the Lamies data set, and I got it from the R package Sombrero. So here, this is the character coappearance network. So, like, you know, if two characters appear in a scene and then they are linked. So the original thing is a graph object. The original data set is a graph object. So what we compute is we compute features of this graph object using, you know, we use centrality, transitivity, closeness, betweenness, degree of the nodes, and the average nearest neighbor degree, page rank, these kinds of things. So the features were motivated from one of Wilkinson's papers. That was in the HD Outliers Wilkinson's paper. And we compute these features. Now, after we computed these features, this data set is no longer, like, you know, this is transformed from a graph object to a rectangular data set. And then we do an O3 plot of this. And again, we see, so these are the variables of the data set. And then these are the characters, which are the observations. And we see Valjean is very much an outlier. So this is three methods worked on it, and if it's an outlier using all three methods, it comes in red, and if it's by two, it comes in orange. And then we have Muriel and all these other characters coming this way, less outlying. And in our Dobin plot, we get Valjean way out there, and then also we have Muriel, Fantine, and all these other characters clustering somewhere here, but closer to this, but still a little bit away, and then we have the rest of the cluster to go on. So again, the Dobin plot agrees with the O3 plot. The next example is using classics from Gutenberg. So we downloaded 22 classics from the Gutenberg project, and it's got lots of classics. Again, this example was also motivated by Wilkinson's HD Outlier paper. So we have all these classics in here, and what we did was we stripped the words from the classics and then removed all the stop words and numbers, and then we did stemming, and then computed a TF-IDF measure, which is kind of a standard measure to compare documents in a corpus of documents. And when we do that, then we convert the 22 classics to a data frame or a data set, a rectangular data set. So here what we have is, again, using the O3 plot. So what we have is these are the variables, and here we have the novels, the classics, and we see that Ulysses is really highlighted as an outlier, and the rest, it's highlighted as an outlier in a lot of subspaces here, and in here we see again Ulysses comes way away from the rest of the classics in our Dobin plot. So again, Dobin plot agrees with the O3 plot. In kind of it brings the outliers to the front and shows, okay, in this projection the outliers are at the front. And so the uses of Dobin, we can use it as a dimension. It's meant to be used as a dimension reduction tool for outlier detection. So it doesn't need to be just 2 dimensions. We can use it in many other dimensions because it does give you a basis. And also we can use it to visualize outliers. So it's a direct projection. It's not an embedding, it's a direct projection. Thank you so much. So the R package of Dobin is on CRAN, and the paper is on ResearchGate. And thanks for listening.